Hey folks, we're going to come back with the second part of our look at gravitation and planetary motion by looking at the universal law of gravitation and the rationale behind why the acceleration due to gravity is 9.81 meters per second per second. Now it all starts with Isaac Newton, right? This smug looking individual with the super perm looking hair over there. He shows up just after Kepler. He wanted to look at, well, why are the planets behaving in these elliptical patterns? So I was able to look at how planets were moving and set out to figure out why. And the big thing that he really wanted to do was figure out how those forces changed based on masses of objects and based on distances between objects. And he was able to use that information to develop what is now known as the universal law of gravitation. The universal law of gravitation states that all objects are going to attract one another so long as they have mass, and that it is going to be proportional to their masses and inversely proportional to the square of the distances. So this is an inverse square law. However, he couldn't find a way to quantify it. He could get it conceptually, right? He could get it qualitatively, but not quantitatively. He could not decipher the exact amount of force, but he was able to figure out that, hey, this attractive force between two masses goes up as their masses increase, and it goes down with their distance, but it went exponentially down as that distance increased, or it increased exponentially as they got closer. So as we look here with this law of gravitation, it describes how the attractive forces of gravitation work, and that gravity is only going to act to attract objects. It will never repel, it will only attract. What we see in terms of the qualitative side here, so the left-hand column on this picture will show the effect of mass, and the right-hand column shows the effect of distance. Each one has a standard mass and distance between them, which will give us some amount of force. What we see in the left-hand column is if you change your masses, you're going to see a direct relationship with the change in the amount of force. Double one mass, 2 times the force. Triple a mass, 3 times the force. Double both, 4 times the amount of force compared to what it was before. Now the effective distance, this is where we see our inverse square. So if we double the distance, we have a quarter the force. So it's 2 squared would get you 4. We're further away, so it will be 1/4. If we get closer, so if we are half the distance, well, if you square that half, you're going to get a quarter, but it's an inverse, so we're going to be 4 times. What we see in the bottom right is now we see double the distance and double each mass. So if we double the distance, we should have a quarter the force. Each of the masses are double, so we'll have 4 times the amount of force. So if we double the masses and double the distance, we get the same effect as if they were the original distance and the original masses. Again, Newton couldn't figure out how to make this an equality, so we settle with proportional. And that's what that symbol is in the equation, that almost complete infinity sign, that is the proportional, right? So he found that it's proportional to the product of the masses and inversely proportional to the square of the distance. Couldn't figure out how to make it an equality until Henry Cavendish shows up in 1798. And he uses what's called a torsion scale or a torque scale in order to determine what that constant ends up being, to be able to quantify the amount of attractive gravitational force between two objects with mass. How this works, if you look at the simulation here, we have 2 large yellow spheres and then 2 smaller green spheres. And the green spheres are able to move based on this twisted wire that is connected to a stationary point. The yellow large masses swing and change where they're located, and the amount of attraction between the small sphere and the large sphere is able to occur, which then causes this scale to move a little bit, and this laser is going to shift from one side to the other based on the attraction. So we're going to see they're attracted to one another, so it's going to get closer. And he was able to measure with a high degree of precision, and he was able to find that this universal gravitational constant, as it is now called, or big G, as we like to affectionately call it, is 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. Don't worry about the units of that number. You will never be tested on them. You're not going to be expected to know them, but those are the units of the universal gravitational constant. So in any formula where you see big G by itself, 6.67 times 10 to the negative 11th is what plugs in there. And that was able to fill in very nicely into the proportion for the universal law of gravitation to now give us the full-fledged equation, which is big G times the product of the masses divided by the square of the distance will give us the amount of attractive gravitational force between two objects, which is F of G. So the universal law of gravitation, big G, m1, m2 over r squared. Example. What is the mass of our planet if we assume a 1 kilogram mass is accelerated at 9.81 meters per second on the surface, given the radius of our planet is 6.37 times 10 to the 6th meters? How we would approach this problem. First, here's what we're given and here's what we know. The universal law of gravitation on top. Big G, we will always know and you will always be given. Now, I'm establishing that the force due to gravity, the attractive gravitational force, is 9.81 newtons because the mass of 1 kilogram is accelerated at 9.81 meters per second. That's the weight of the object, and the weight is actually going to be the amount of gravitational attraction between the Earth and this mass. We also know the mass of the object is 1 kilogram. So what we're trying to find is the mass of the Earth, m2. When we rearrange the universal law of gravitation to solve for m2, right, what we find is that we take our force times the square of the radius divided by big G divided by the mass of our object. So we just rearrange the universal law of gravitation, and when we solve this out, we get 5.97 times 10 to the 24th kilograms. Now another example, what is the gravitational force on a 91.7 kilogram object when on the surface of our moon? So now we're looking for F of G on the moon, given the constants up there for the radius of the moon and the mass of the moon itself. So again, what we are given is the universal law of gravitation. We know big G, we know the mass of both objects, we know the radius of the moon, which is technically going to be the distance between them. That's the thing with the universal law of gravitation, is that r is the distance between the center of mass of two objects. So when we're looking at the moon, for example here, we'd be looking at the center mass of the moon, which is roughly the center of the moon, out to where you are on the surface. So really, the radius of the moon is the distance between two objects. You could use that r as the distance between two people, right? So we could have m1, m2 are the masses of people, and r could be the distance between them, and we could find the gravitational attraction that exists between them. Now here we don't need to rearrange the formula because we're looking for the attractive force between them. So we have big G, we have our two masses, the mass of the object and the mass of the moon, and then we have the distance between their center of masses, which in this case would be equivalent to the radius of the moon. Note that we have to square that value, and we get the attractive gravitational force between these two objects is 148 newtons. So we have this big G, which then brings us back, well then what's little g? Like, yeah, little g is the acceleration due to gravity or the acceleration caused by gravity. Same thing. Remember, little g is not gravity. Gravity is the attractive force between two objects. Little g is the acceleration that is the result of that gravitational force. We could technically consider this to be the gravitational field strength that acts on an object, where the closer you are to an object, the more attracted you are to it. The further away you are from the object, the less attracted you are to it. So really, this newtons per kilogram that we can consider little g is telling us this is how much force is acting on an object per kilogram of mass. And when you break down newtons per kilogram, you do actually get meters per second because you take the newton, which is the kilogram meter per second squared, divided by kilograms. The kilograms drop out, you're left with meters per second squared, which is acceleration. But ultimately, it's how many newtons of force are pulling on this object per kilogram of mass that it has. And this changes depending on where you're at in the universe and, quite frankly, where you're at on a planet. The further away you get away from the center of mass of that planet, the lower your gravitational field strength is. Closer to the center, higher G. Further away, lower G. Which is then interesting because you get the idea of 0G and being in orbit and, oh wow, there's no gravity in space. It's like, well, you are still under the influence of gravity, right? Gravity doesn't stop acting just because you get above the clouds or just because you get into outer space. You still are being attracted to that planet. If the moon is attracted to the Earth due to gravitational pull, there is certainly a gravitational pull on satellites in orbit, which means the astronauts are indeed under the influence of a gravitational pull. So why G is 9.81 is actually pretty substantial, and it's one of my favorite proofs that we see in physics. We have two different ways that we can describe the attractive force that's existing on an object. The weight, which is mass times the acceleration due to gravity, or the universal law of gravitation. Notice here that the attraction between two objects, right, the mass of an object, and here we're going to go with the mass of the Earth, those are our two objects that we're going to look at for why G is 9.81 on Earth. If we set those two equal to each other, which we can do because technically they're both solving for an attractive force, right, the force due to gravity that is acting between objects, we can set them equal and see that, hey, the mass of the object cancels. So again, we have another situation where the mass of an individual object doesn't matter. Your mass has zero bearing on how strong the gravitational field is on the planet. None. No bearing at all. Really, what we see in this formula at the end, where little g equals big G times the mass of the Earth over r squared, that's telling you that what truly influences the acceleration due to gravity is the mass of the planet and the radius of the planet. Technically, you could curl yourself up into a little ball. You could find your mass and you could find your radius as you curl into a circle, and you could figure out what your gravitational field strength is. Nothing wrong with that. So on Earth, when we use the radius of the Earth, big G, and the mass of the Earth, we work through that formula and we see that little g is 9.81 newtons per kilogram. Again, using the mass of the Earth and the radius of the Earth, we can get to that proper value. So again, very cool idea that the mass of an object that is being pulled on by the planet does not influence its own rate of acceleration. Helps go back to the idea of projectile motion and freefall motion, where the mass of the object didn't matter. This is why it didn't matter. So the Earth is not a perfect sphere. It's not, right? It is not a perfect sphere. It's, it's got hills and valleys and mountains and right plateaus, and it's got plenty of geographical features that influence it. So really, the acceleration due to gravity or the gravitational field strength changes depending on your location, as was previously talked about. So the furthest location from the center of the planet is Mount Chimborazo, and the closest spot is the bottom of the Arctic Ocean. Obviously, we would have to get rid of pressure due to the water that would be above you, but if we were to drain the planet, we would see those are the maximum and minimum values from the center of the planet. So at the maximum value on the left-hand side, at the furthest value, so the maximum distance, G comes out to be 9.77 newtons per kilogram. And when we're the closest to the center, so the minimum distance there, we see that little g comes out to be 9.87 newtons per kilogram. So not a huge difference between them, but we would notice a little bit of a difference in how things move, because that 0.1 newtons per kilogram on a big scale can turn out to be very, very powerful and very meaningful. So here we see some of the history behind the universal law of gravitation, which is still in use today, as well as a backstory and a rationale behind the gravitational field strength of a planet. Thanks, guys.